This is my final project video for ENME 49Y, Remote Sensing at the University of Maryland. Throughout the semester, the goal of the course was to assemble, calibrate, and deploy a portable and affordable LiDAR sensor, exposing students to the field and preparing us for the rapidly evolving world of engineering. This project integrated our skills in optics, electronics, and software in order to 3D map an object on the university campus, giving us hands-on experience with this exciting technology. This video will document the steps taken to prepare the sensor setup, map the target, and process the data. My target of choice is a wooden bench located behind Tawes Hall, shown here. This target presented several advantages for mapping. First, the target is in a secluded area with little foot traffic, making it easy to work on without being disturbed. Additionally, the area has low levels of ambient lighting, reducing noise and allowing for higher quality scans. An unexpected benefit was the bricks on the ground of the surrounding courtyard. Having grooves on the ground made it easy to map on straight lines with right angles. This allowed for easier data processing later on by keeping each face of the object at a known angle to the sensor. All LiDAR systems have transmitters, emitters of photons that interact with the target of interest, and receivers, lenses that resolve data about that target once that light has been reflected back. This will be explored in greater detail later, but for now this is one example of a LiDAR sensor. This is the sensor that I've built and worked on throughout the entire semester and used for this project. So let's go through the components together. Mechanically, the white mount that houses the components is made from 3D printed PLA. The mount was printed in two halves which were then joined together using superglue. Each of the components on the sensor are held in place using a combination of glue, tape, zip ties, and twisted wires. The transmitter of the sensor is a line laser, pictured here and held in place with superglue. The laser is powered using 5 volts from an Arduino Uno. The laser itself is exactly 12 inches apart from the receiver, a Raspberry Pi camera. The camera and the Raspberry Pi taken together take scans of the target object which can then be processed later. In order to process that data correctly, it's necessary to know the angle of the sensor to the ground. For my LiDAR deployment, I used a cell phone and the Bubble Level app to measure angles to the 10th of a degree. Remote sensing refers to the process of acquiring data about a target without physically coming in contact with it. The field can be broken down into both passive and active remote sensing. Passive sensing employs no man-made transmitter and relies solely on naturally occurring radiation. An example would be taking weather readings using satellites. Active sensing requires the use of an independent transmitter or energy source. One example of active remote sensing is LiDAR, or light imaging, detection, and ranging. LiDAR works by sending a pulse of photons to interact with a target of interest, some of which are then reflected back to a receiver and sent for data processing. LiDAR is governed by many variables which are encompassed in the LiDAR equation. The number of photons you can expect to receive back from the target for a given pulse depends on factors such as the number of photons sent, scattering coefficients, the area of the lens detecting the photons, noise, and more. Another critical principle is the range equation, which is used to extrapolate distances based on the amount of time it takes for transmitted photons to return. The semester-long project is an example of LiDAR and active remote sensing. Acquiring data for the project requires the use of a laser, which is an active transmitter of energy. However, the project is truly a tandem of LiDAR and computer vision, which is another type of remote sensing. Computer vision deals with the acquisition and processing of digital images and videos using computers. In the scope of this project, the use of a line laser is an example of LiDAR, using emitted visible light to scan an object. The light reflected from the target is then received by the Raspberry Pi camera. Computer vision comes into play with the Raspberry Pi as well, which uses Python and OpenCV for processing the data acquired. The LiDAR sensor is driven by Python code with the Raspberry Pi, as well as OpenCV, an installed computer vision package. In order to use the sensor for 3D scanning, however, some calibration must be performed. The system isn't ready to go right away. Preliminary calibration included using a single-point laser beam separated from the camera's central axis by 12 inches. The laser was turned on and a piece of paper was held at 6-inch increments away from the camera ranging from 10 to 0 feet. Rather than moving the sensor setup, which was not yet mechanically integrated into a mount, it was easier to move a piece of paper acting as the target instead. As shown in the video, the laser dot moves farther and farther off screen as time goes on, corresponding to me moving the paper closer to the camera. This is because of the geometrical LiDAR technique. As the target moves farther away, the angle from the camera's lens to the laser point decreases based on simple trigonometry, making the laser seem more in line with the camera despite being physically offset by 12 inches. By this principle, it's useful to measure the pixel location of the laser point in the horizontal direction as it moves, equating the pixel location to the known distance at which it was measured. Using a Python script, these values were compiled into a calibration curve which demonstrates the accuracy of the system. More thorough explanations of the Python scripts will occur in the next steps. In order to calibrate my field deployable sensor, similar testing was done with the line laser. The LiDAR setup was oriented perpendicular to the wall using a tape measure to mark off 6-inch increments. As you can see in the following images, the same geometrical LiDAR technique applies. The farther the sensor moves away from the wall, the more the line laser converges towards the pixel center line in the camera frame. Each of these images was run through the laser alignment Python script, which performs a few functions. First, the code uses an HSV color segmenting mask to pick out the red laser of interest. All other colors outside of this range of values are rejected. The remaining laser pixels are then averaged together to find a central one, whose x-pixel coordinate changes due to the geometrical effects. The x-pixel location moves towards the edge of the screen, pixel 0, the closer the sensor gets to the wall. These pixel locations are then plotted against the distances from the wall to create a calibration curve with tweakable rho and RPC values. Using a rho of negative 0.0001 and an RPC of 0.00008 makes the data fit very well. Now that sensor calibration is complete, I'm ready to collect data. Although scans taken for data processing were recorded at nighttime for optimal laser viewing conditions, the following segment serves as a demonstration of the data collection process. The LiDAR sensor is connected to a tripod for acquiring scans of the object at various angles. The connection is secured using another 3D printed component. The Raspberry Pi is powered through an external charger, secured to the mount using painter's tape. The Raspberry Pi is controlled using a virtual connection to my laptop with an Ethernet cable. The Arduino powering the laser is powered through a USB port on my laptop. Data was collected from the bottom to top of the bench at 1 degree increments, the highest resolution the Python code would allow. The angles were recorded using the cell phone app and then input into the data generation code. For each angle of interest, an image of the target with the laser being shown was recorded for later processing until the entire face of the object had been scanned. The following scans were taken at nighttime and correspond to one of the side faces of the bench as just previously shown, mapped from bottom to top. The laser is clearly visible, with slight noise from other lighting that can be segmented out later. The angles on the scans are entered as positive angles from 0. For example, 350 degrees is the same as negative 10 degrees. These scans are then imported into PyCharm for further processing. The images from data acquisition are imported into PyCharm for use using this pointer. The code generates a text file containing XYZ coordinates which can be manipulated in MATLAB and other softwares. The code also takes a few input parameters of note. For example, in order to pick out the laser light specifically, an HSV color mask is used to segment the image, filtering out anything but red. The code also takes the rho and RPC values that were required from sensor calibration earlier. The laser's range in the image, or the distance away from the camera, can then be calculated using these parameters as well as the pixel distance away from the center line of the image. The previous calibration curve that was fit with rho and RPC for my particular sensor equates that pixel distance to a measurable range value. Using all of this information and the angles recorded during scanning, the XYZ coordinates of laser returns are calculated using trigonometry. These coordinates are stored as column vectors in a text file separated by commas. Running the code shows that each image gets parsed through individually before compiling all calculated coordinates into a visible point cloud. One issue that I ran into with the remaining mapping of the 3 sides of my target object was that the longer, wider faces of the object, so the front of the bench and the back of the bench, were actually wide enough that in order to keep it entirely in the camera frame, I had to move the sensor far enough back that it was pushing the limits of the calibration curve. So in order to get around this, I decided to flip the sensor on its side and rotate it from left to right, panning instead of scanning up and down. As you can see, the entire setup has been rotated 90 degrees, allowing the sensor to pan from left to right. To acquire angles for these scans, I used a compass app instead of the bubble level. Because of the new orientation of the sensor, the points generated for the front and back faces needed to be rotated into place for the 3D point cloud. The other side face was mapped the same as the first. Running all 4 sets of scans through PyCharm yielded 4 different text files that could all be manipulated together in MATLAB. The 4 text files generated in PyCharm are imported using the import data command, one for each face of the object. The files had to be pulled from the same subfolder as the MATLAB code running the script. Each text file was manipulated independently, filtering out unwanted points by eliminating rows of points outside of desired X, Y, or Z coordinates. The scans were also rotated into the proper orientation using rotation matrices that corresponded to the desired angular offset. Following these two steps, each dataset was then offset by necessary x, y, and z coordinates to stitch the scans together into one cohesive point cloud. The four matrices that were being manipulated independently were then combined into a single matrix in order to run the code. Prior to filtering, the point cloud looked like this. It's difficult to see what the object looks like without zooming in due to substantial noise. However, after filtering, the point cloud becomes more visible. Unfortunately, the front and back faces of the object are still fairly warped. I attribute this to inconsistent angle measurements in the Compass app, which I found to be less accurate than the Bubble Level app. Improper angle measurements would cause errors in the point cloud, because the coordinates are calculated in the Python code using these exact angles. I decided to switch back to using the Bubble Level app, which required a new approach for mapping. In order to use the Bubble Level angle measurements instead of the Compass angle measurements, I had to flip the sensor back to its original orientation of scanning up and down. However, in doing so, to get the desired resolution, I had to move the sensor closer to the target object, effectively cutting off part of the bench from the camera frame. To fix this issue, I decided to map each of the wider faces, so the front, the back, and the seat of the bench, in two halves and stitch them together in MATLAB rather than trying to do them all in one go. The way that I went about doing this was by taping a dull ruler to the backboard at the exact middle of the target. After taking scans and processing them through PyCharm and MATLAB, I would look for the ruler to show up in the point cloud, filtering it out along with everything beyond it that didn't contribute to the half of the face that I was trying to scan. After scanning the left and right side of the target normally, and scanning the front, back, and bench seat in two halves each, I generated 8 total text files. These files were manipulated using the same methods discussed before, filtering, rotation, and linear offsets. In order to demonstrate the 8 different faces, this is an exploded view point cloud. I opted to remove the slats from the front face scan, leaving only the posts, because the back face scans provided enough resolution as it was. Stitching the 8 faces together yields my final point cloud, which shows significantly improved resolution. Comparing the final point cloud to reality shows that the point cloud holds up favorably. Overlaying the point cloud with images of the target shows that on the right side, everything lines up, including the posts, armrests, and backboard. Looking at the bench head-on shows that the posts and slats all line up perfectly. However, the point cloud fails to recreate the same depth that the image has because the cloud is strictly into and out of the page. Comparing measurements of width, depth, and height also showed that the scans are of good quality. Measurements taken in MATLAB were only 1 to 6 inches removed from the actual dimensions of the target. To create a 3D mesh, the point cloud was imported into Cloud Compare. After selecting the point cloud, normals were estimated with a neighborhood value of 1200. A Poisson surface was then constructed using those normals. Excess material was cut by segmenting the mesh and deleting unwanted regions. A few example cuts are shown in this video. After proceeding with more cuts, including slicing out each slat in the backboard, this is my final 3D mesh. Further work could be done to fill in some missing points, but overall this mesh is very representative of my target object. For converting the mesh to a printable STL file, I used an older mesh from MeshLab that had fewer holes. Importing into Creo was simple, and the mesh was edited to add the appropriate amount of thickness for printing and was then saved as an STL file.